get that going sooner rather than later. And then once you guys get the final going, it's just a matter of doing it up. Then the group version is going to be open for the second part of the week, and you guys can group yourselves up however you want. And yeah, any questions, comments, concerns you guys want to go through? I've got the review open in another tab, so I can pull that up for everybody. And yeah, how are we doing this morning, guys? Anybody out there? Is my connection pretty bad so you guys can't really hear me? It's not a bad idea. So, okay, if we don't have any questions, we don't have anything that you guys want to go ahead and review, I'm just going to go ahead and share screen for a moment. And remember, if you look at the formula, it means the velocity is going to have to have increased by the square root of 1. Never. Resisting movement. Pressure, obviously, in fluid that happens to be giving us way to what gives us buoyancy, is the air that's pushed underneath us, specifically enough that it's actually giving us a vertical displacement against gravity. Make sure you guys remember when we talk about scapular abduction, or sorry, protraction, retraction, and then elevation, depression, upward and downward rotation, along with we can have forward and posterior tilt. So cervical is usually, typically, you would define it as a lordic, not a lordosis. Same thing with lumbar. Thoracic is going to be kyphotic, but not full kyphosis. And then sacral is fused. Yep. As the angle increases more, the greater amount of force is going to absorb. This is going to be from the passive elements, specifically from both the passive series and then passive parallel, series being tendon, and then the series being tendon, parallel being muscle. One thing that was really cool this weekend, I got to be on a teleconference where we actually got to learn a lot of interesting things about tendon from some presentation over or by a DPT about how tendons effectively are going to go through loading, which was really neat. And I'll pull up his slides that I took pictures of. One thing that I thought was pretty interesting that the gentleman put up is he was talking about when you're looking at tendons, and that should be shearing, but it turns out I was typing things pretty, but the junction between tendon and muscle is put together like Velcro. So hence, it's meant to deal with pulling across, but if you pull on an angle, you can literally tear it right off. So he showed a video of someone doing a jump start, and literally it was like right off the ground behind them, and you see this gal's calf just roll up. She definitely ruptured her tendon there, and it was slightly nauseating, but also just really fascinating. So what was interesting is since it's viscoelastic, that means the harder you pull on the tendon, the stiffer it actually becomes. And stiffer gives you better force transfer. However, what happens if you go and test it obviously too hard, it doesn't absorb force, and that's where it's just going to rupture. And so some of the interesting differences between a normal tendon and then abnormal tendon. And then what was really, I thought was interesting was for the remodeling, that it looks like some of the research for tendon loading is in reality, it only effectively is going to be modified but for about 10 minutes. And then after that, you're not actually getting any more increase in turnover. So in reality, when you're looking at tendinous rehab, it looks like doing a greater amount of dosage, meaning frequency, and with shorter duration is actually the more effective way to modulate it. Because when it comes to like muscle, you're going to be able to effectively, from resistance training, from plyometrics, endurance training, etc., those sessions can last obviously hours, and you're generating those signals to a greater degree over time. Now, at some point, you peak it out with the greatest amount of signal you're going to send, but you're not going to probably max out muscle protein synthesis capabilities of an entire muscle group in 10 minutes over an entire, if that's your entire workout. So I thought that was pretty fascinating. And hopefully somebody did too. Or once again, my Zoom is doing a very, very poor job. So we're not able to, you guys aren't able to hear me too much. So that's okay. Yeah. Fast twitch, more muscle fibers per motor unit, higher power output, higher, essentially faster fatigue, prefer glucose and specifically anaerobic glycolysis. Okay, where the Atlas is effectively only going to go ahead and give you flexion extension. Axis is where we're going to get rotation, a little lateral. You need to be laying down or decompressing. This is going to be the knee buckling in. Varus is going to be the knee buckling out. Magnus Effect is going to be the combination of those forces that's going to cause us to move in one direction or the other, thanks to effectively the displacement of air due to rotation of an object through the air or through fluid. Meniscus is increasing the surface contact between your knees, is specifically your tibia and femur, and that's going to allow for a little bit more comfort with movement. This is going to be the giant band of connective tissue through the bottom of your foot that's helping with elastic recoil in your foot, which is a good thing, along with it's also going to be giving us a little bit of stability. Tibial torsion is going to be that rotation, just like we can have a little bit of femoral torsion. Then math. Okay, so since you guys don't have any questions, or at least I can't.
Can you go over number 27?
Awesome, thank you. Okay. All right, so let's go ahead and look at it. So we're going to start off, we're going to say the force is going to be now multiplied by okay, so the biceps attachment is just 1 centimeter. So convert that into meters just because, to make life easy, equals R, and we're going to have to come back to that F. So we've got 0.1 meters, so 10 centimeters for the weight, and that's going to be equal to 10 kilograms, which we're then going to multiply by that 9.81 meters per second squared. And then we're going to add a 0.05 meters multiplied by the 5 kilograms, which will be multiplied by 9.81 meters per second squared. And so once we go ahead and solve for all this, now we're going to go ahead and be onto our happy little figuring out for the force. Now it's going to be the 45-degree angle. So since it's pulling on a 45 and it's not pulling straight vertically, we're going to have to solve for the opposite. So we're going to have sine of 45 degrees, and we're solving for the hypotenuse. So we're going to actually have the F from before, F divided by the sine of 45 degrees can equal the biceps pulling force. Does that make sense?
Yeah, thank you.
Anytime. That's okay over there, honey? Just fighting? Okay. Got them all riled up with the laser pointer earlier. Okay. So, flexion here. Yeah, that's easy. That's just 10 times 1 squared times 9.81. Yeah, actually, so we don't need that. Well, that's really easy. I need to make more difficult questions. I feel like this is too easy. All right, so if you guys don't have any more questions, you guys want me to go and review?
I have one more question. For like 42 and 43, when it talks about the fiber arrangements,
Yeah.
is that referring to like slow twitch and like fast twitch fibers, or is this something else?
That's referring to, remember, pennation. So pennated fibers and then longitudinal fibers. So the muscles
Okay.
have just the straight long, so they're not pennate, they're just essentially linear arrangement. Those are going to be naturally faster, but the ones that are pennated are going to have a greater force production.
Okay.
Good question. And this is going to be the long head of the biceps femoris, semitendinous, and semimembranous. Really, it's everything except for the short head of the biceps. All right, well, if there's no more questions, then I am going to, let's go ahead and give me some scene from an action movie or otherwise that I can try to pull up on YouTube, and we're going to have a little bit of fun with physics. Sounds good. Okay, so I've got it from here. Now you're gonna have to tell me what you're referring to exactly.
I think it's like near the end. Like, I think it's like 1 minute and 17 seconds.
Right there?
Yeah.
Oh man, this is gonna get weird. Okay, cool. So how much do somebody go up and throw up in the chat how much Thor is supposed to weigh in, you know, the Marvel canon? And of course my meeting controls aren't coming up, because that would be too useful to me. Okay. Okay, so 640 pounds. Oh, let's have some fun with this, Kylie. Let's have some fun. Okay, so if we're gonna go ahead and now move this over here so I can see what's going on. We're gonna go ahead, take our speed, decrease that down to quarter speed, and okay, so let's go ahead and it's gonna be a jump and start. Oh, Jesus. Okay, so hops off the ground. Thank you, honey. What looks like to me. Sorry, the cat sprinting through the house almost just took out my wife. Okay, so it really looks like it took him only maybe, since we're going quarter speed, and he got off that ground real fast, and that's with a single leg too, mind you. 10th of a second, jumps off the ground, and let's ballpark this height. That looks like a good, we'll say 20 odd feet in the air. So we can go ahead and convert that into 6 or 7 meters. Okay, so we figure 10th of a second, go up 7 meters. Kinetic energy equals 1/2 of the mass times the velocity squared equals the mass times the gravity, which is going to be 9.81, the height, which is going to be 7 meters. So masses cancel. So if you take 7 times 9.81 times 2 and then the square root of it, that's going to give you the initial velocity. So if you take that velocity and divide it by 0.1, you'll have his acceleration. And then if you take that mass of him being 670, so you take that 670 divided by 2.2, you're going to then go ahead and convert that on over into kilograms. You multiply that by the acceleration you solved for, and now you have the force you put in the ground to jump off the ground, which is going to be ridiculous but fun. So now, okay, so we're about, let me come back just a hair, goes, okay, hits the ground, okay, and God, that's the same thing as the 10th of a second, and then blows everything backwards. And okay, about how far do we think every one of those dudes just got shot backwards through the air? And you guys can throw up your opinion in the chat, because we are obviously in the realm of just absurdity, but I'm having fun with it. Nothing, guys? Okay. Now, that's problematic. Okay, so 30, 40 feet, meh. Yeah, I was gonna at least say over 10, maybe 15. Now, this is problematic because notice there's electricity, so technically, if everyone's getting hit by lightning, it's not really Thor's hammer or Thor hitting them with the concussion of the blast or the hit to the ground like a shockwave. Instead, it could just be all of them being electrocuted, so their muscles are contracting involuntarily, and that's propelling them through the air. But then again, since a lot of them were coming forward, in theory, they would have jumped into him and not backwards. So, boy, that gets really weird really fast. Okay, so let's just go ahead and we'll split the difference and say it was about 25 feet, which means we're going to be dealing with effectively, we'll say it's about 8 meters. So if each of those guys got blown back 8 meters, they happen to fly that distance in, come backwards a little bit. Good Lord, it's going to be less than a second. So if we go ahead and you go start, and then stop. So maybe about, looks like 1.5 seconds for them to be thrown backwards. And if we watch that again, because we're going to be doing this a lot, we're going to notice it looks like they're all initially, running in towards them, and that literally stops their entire momentum and turns them around. So if you figure they go backwards 8 meters in 1.5 seconds, then you can go ahead, and that's going to be their velocity from the second half. And let's say they were running in at 2 meters per second. So effectively, they're going in, getting blown backwards. So you got effectively a full change in acceleration of going from, we'll call it -2 meters per second, and then going to a positive 8 divided by 1.5, and I'm being lazy this morning, which, okay, let's just do the math. That ends up with 1, 2, 3, 4, 5.33 meters per second. So we're talking about a net change of 7.33 meters per second. And that's occurring in effectively, we're going to say maybe a quarter of a second. And you guys could use your own math for how much that reversal takes. So you then just need to figure out the mass of each of those. Oh God, this is going to get weird. Okay, so they look pretty big. Like if I'm a 200-pound guy, they look like they're way more than I would. So we're going to figure they're each going to weigh at least, we'll say about 120 kilos each. So if you got 120 kg multiplied by 7.33 divided by 0.25, you have the total amount of force required to accelerate the object, aka their body, in that period of time, but there's more than one of them. So, oh man. So I mean, right there, you figure 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh yeah, that's 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Yeah, that's a lot of them. Oh, actually, this might be an easier view to go. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Dang it. Okay, so you figure if it's 32 of them, multiplied by their mass multiplied by gravity, sorry, not gravity in this case, we've got the acceleration that they are incurring due to the change in their velocity. So what we literally are going to have there is the total amount of force required, which is going to be quite large, because we're looking at 0.25, so that's 29.33 meters per second squared, multiplied by 120 kilos, which that might be underestimating it. I would look up and figure out A, what the heck those guys are called, and then B, anything they might have for how much they're supposed to weigh, because that's going to give you better information. Times 32, so yeah, you're looking at well over 100, sorry, well over 1,000. Oh my God. Yeah, so that's going to be close to, it's going to be over 100,000 newtons of force. Sweet. So, good. Nice choice there, Kylie. That was fun. What other questions you guys want to go ahead and try to work through?
For the first part, when you were finding out the initial velocity, you said you used the kinetic energy equation of the 1/2 mv squared and then gravity times mass times height. Okay, and then okay. And then for the second part, did you use that same equation for those people to find out initial velocity? Or were you trying to find out acceleration?
So I instead was just looking at effectively, we ballparked the distance they covered in that period of time, and then divided it by effectively the time it took them to travel that distance, getting blown backwards. So that gives you the velocity. And then obviously the acceleration component is going to be how quickly they went from the previous velocity of going forward to the new velocity of getting blown backwards.
Okay.
So it's the one, effectively the two being added together, because you have the one velocity would be considered negative in this example, and then them being shot backwards would be positive.
Okay. Thank you.
Hey, no problem, Sydney. Any other examples you guys want me to try to work through from any form of media that I can get up here and maybe get in some copyright trouble with groups from having used on a quasi-educational conversation? I guess I'll leave it up there.
Can we do a scene from Deadpool?
Which one?
Don't matter. Just any scene.
Don't matter. Oh man. Well, I have no idea what we're about to be in for here, guys. So I'm going to say I'm sorry initially. This is all Cameron's idea. All right. So, and we got ourselves a winner. So, Wade Wilson starts off on the ground. And let's go ahead, guys. In the chat, I want you to put up okay, so accelerates in, yeah, 1/10 of a second. That looks like a 3rd story. And then goes into a nice wall. Okay. And then he jumps down from the 3rd story. So, okay. Deadpool, I think canonically, is actually supposed to be somewhat close to my own body weight. So you think he's supposed to be like a 200-pound guy, but he's supposed to be taller and obviously better looking. Now, if you're thinking about just the jumping down from the 3rd story, well, okay, each story we're going to say is usually about 3 to 4 meters. And so we can figure maybe that's about 4 meters. So he falls 12 meters. So he then has to deal with gravity and obviously his mass, which we'll say it's about 100 kilograms just to make life kind of easy. So 100 times 9.81 times 12 meters is going to give us that potential energy. And we're obviously going to convert that into kinetic energy. So now we're going to multiply that by 2, take the square root of it, and then we can divide out the 100, and that's going to give us the velocity he hits the ground with. And so, backtrack just a little bit. If he goes and he jumps back down, and it looks like he stops himself in maybe a 1/4 of a second, if that. And you guys can come up with your own values there. So we're going to go with that divided by is going to give us his total acceleration. If we have that time from the previous velocity that we already got from the kinetic energy potential energy equation. And we're going to go ahead and now take that, multiply it by his mass, which is 100. And then we have the amount of force that he would hit the ground with. And then you can multiply that number by 0.88, and that would be the force effectively going through his knees. Math, because we subtracted the weight of the lower extremities. So you can literally figure out how much landing like that is hell on your knees. Now, let's go back to the little bit more fun, which is him getting propelled through the air. So, okay, we got about 3 stories, but how far does it look like he gets shot back through the air? So he's going upwards at least 3 stories, and he's flying. God, how far would you guys say that really is horizontally? Well, to be fair, if we're going to base that off of we can just say it looks like he's flying at about almost a perfect 45-degree angle. So if we've got 3 stories upwards, now we can just use trig, so we can figure that he's got effectively, take that 45-degree angle. So I can just go ahead and use, so if we've got a right triangle and we've gone 3 meters upwards, well, that's just going to be a squared plus b squared equals c squared. So we figure both sides are going to be equal, quad line, in this example. So that's going to end up with 3 squared plus 3 squared, so 9 plus 9, 18. Square root of that is going to be, oh my gosh, it's probably like it's around 4.2-ish. But still, you've got the square root of 18. And he goes and he flies that distance in, let's see here. So we watch the clock, start. And stop. It looks like a good 1.5 seconds. So if you take, now you've got the square root of 18, because that's our distance over the time, which is going to be about, say, 1.5 seconds. you've got his velocity. Now he changes from 0 to that velocity, and that's the average velocity over the time period, because he would have been deaccelerating the entire time, which we can do that if you guys would like. Yeah, let's do it. It's gonna be fun. Okay, so we've got that velocity over the entire time period, but that is the average, which in reality, we're going to have the good old projectile motion equation. So our x term is going to be that 12 meters equals v sub o times time, which is going to be 1.25 minus 1/2 of 9.81, because that's going to be acceleration, meters per second squared, times 1.25 squared, and then that is going to give us our initial velocity if we solve for that. So I'm doing all this stuff on a scratch sheet of paper. And then once you solve for that initial velocity, well, now we take that initial velocity and we're going to divide that by that, gosh, 0.2 of a second maybe or so that it took for him to get accelerated up to that velocity. And so we'll take that number, multiply that by 100 kilograms, and boom, you've got the force required to launch Deadpool that far. Fun question, Cam. Oh God. Yeah, I'm not gonna do the wood chipper scene. That's a little too dark even for me. So, anything else you guys want me to break down, or you guys doing good?
I got another scene in mind if you want to do another one of these.
Yeah, we can do whatever you guys want. It's your guys' review. What are you talking, Cam?
You know the scene from Hancock when he stops the train?
I'm about to. Oh, that guy's in this movie. And you guys like really dark movies, you guys should watch Ozark sometime. Okay. So, number of things to break down there. Okay, so if we go back, right about there is where we want to start off. Now, yeah, I got no idea the speed that this train's going. Okay, so first and foremost, he takes that size of a car, pushes it with just his arms. Yeah, a grand total of what looks like at least 3 meters in the air. So you take the weight of the car, multiply that by the 3 meters, And effectively, he's going to probably have pushed it up there, and you can figure out however long it took him just pushing with his hands, which maybe a couple tenths of a second. You're then going to go ahead and take that velocity for how it would have gone from being upright to sailing through the air at the apex of its flight, and ballparking that velocity with like what we used with the Wade Wilson reference earlier. And yeah, you're going to be able to figure out the amount of force it would have had to apply into the car, which is going to be freaking nothing compared to the train. Now, so the train goes and obviously comes over, hits him, and effectively, good Lord, I mean, that thing stops in half a second, maybe, a full train, which if we go back, it's definitely,
If you go to the end of that video, it's like there's like 30 cars on that train, I'm pretty sure, because it shows them all falling over at the end.
yeah, so then you got to figure out the weight of the locomotive and then the different carts behind. I maybe got too short of a version of this, but that's okay. Yeah, because this one doesn't show it. Yeah. Oh, Total Wine and More. Boy, do they definitely not understand who they're dealing with. Quickly, buy poison. You can't deal with reality, so do drugs, but socially acceptable ones, children. We have a wide variety of different drugs that you can do. Think about how much you don't like your family, your kids, your life, your job. Poison yourself with something that is a pretty potent neurotoxin because it allows you to deal with reality. Well, in the way that you can't really deal with it. Try these fermented dead grapes that we put in yeast and then let sit in barrels for a long period of time. My wife says I ruin things. We've been doing FaceTimes on occasion and talking with their family, and they'll start talking about how much they enjoy different flavors of wine. And otherwise, I'm like, guys, I don't want to hear about your drug use. I want to talk to you guys. Needless to say, that's not very well appreciated. I don't know if you can hear her sighing in the background. She does that a lot, understandably. Yeah, you could also take the single hand grabbing the front, because now it's a leverage problem of grabbing under the bumper and then flipping the car up. So you're going, and that's torque of flipping it up to its end point. And you figure the midpoint of the car is to be the center of its mass. You have the length of the car, flip it on up, boom. You're going to be able to figure out the amount of force required to take it from there to the top, especially because you've got to go across against that 9.81 meters per second squared of acceleration. So it's going to make the math a little bit more complicated, but it's a leverage equation. You guys can go and do that. But yeah, Cam, if you can figure out how many train cars there are, figure out the weight of an average train car, and specifically if it looks like there's any contents that's spilled out or otherwise. But if you put all of those together, the weight of the train, the weight of all the train cars, okay, so then you've got the mass of it, and then you can figure out the velocity to the best of your ability. Remember this, the individual spots, the slats on a train car are uniform in distance. So you can figure out kind of from watching from this scene effectively how fast each of them is ticking by, like right off the nose over here, and you can figure out how fast that train had to be going. So it went from that velocity to 0 in a pretty damn short period of time. So then you take and obviously divide that over the period of time it took to change that velocity from its previous number to 0. You have its acceleration, then you're going to multiply it by that mass, and you now have the force required to stop that train that rapidly, which is going to be a insanely large number. So, questions, comments, concerns? All right, guys. Well, stay safe out there. hope you guys are doing okay. Keep studying for your final. Make sure you got everything else taken care of. You take advantage of the extra credit stuff while you can. More importantly, make sure you're taking care of yourself. And, you know, like we talked about briefly with that commercial, if you're going to use drugs, just make sure you use them in acceptable ways, specifically that you're not drawing a dependence upon them. You're using them only in ways that help enhance your life, not subtracting from it. Because just because a drug is legal doesn't mean it's a good one to use. And I'm not here to get into the conversations about illegal drugs, but anyways, stay safe out there, guys. Miss seeing you guys in person, and have a great day. If you guys don't have anything else, bye-bye.